All right. So yesterday, we started talking about the law of conservation of mechanical energy, okay, which says that in the absence of other forces, okay, or in the absence of non-conservative forces, that our mechanical energy will not change. It can convert from potential to kinetic and kinetic back to potential, but its absolute value cannot change. All right? So a prime example of that could be something like a roller coaster. Okay? So if I'm up here at the top of the first hill, right, I would have, we'll just pick a number. Let's say it's 1,500 joules worth of mechanical energy. At this position, most of that would be what form? Potential or kinetic? Potential. It would be mostly potential up there. Okay, so we'd say, maybe 1,400 of it would be potential and 100 of it would be kinetic. Okay, down here, where I'm back down at ground level, how much of it would be potential? None of it. Right. Okay, if I'm at ground level, I can't fall any further. My height would be 0. So how much kinetic energy would I have there? 1,500 joules. Yeah. Okay. That's a J. I'm still getting used to writing on the new board. I have to pull the pen very far away, and I never do. Okay. So yeah, down here it would be all kinetic. It would be 1,500 joules of kinetic energy. And then right here, okay, I'm a little bit off the ground, but not very far. I'd still be moving fairly fast. We'd probably be looking at, maybe 1,000 of it being kinetic and maybe 500 of it being potential at that position. But the amount of mechanical energy is always the same. Okay, that 1,500 joules is always the same. It always has 1,500 joules of mechanical energy because no energy is being created and no energy is being destroyed. Okay, everybody all right with that idea? Okay, so this would be our simplest example of a law of conservation of mechanical energy question. All right, so if we're looking at this, okay, what I often do, okay, in lots of physics questions, and it's totally okay for you to do this as well, okay, is draw a picture of it. And that's a lot because I don't draw very well. Okay, I mean, you saw yesterday, right? I drew I was just starting to draw this picture at the end of the day. And if I really concentrate, I still look like I have some kind of spinal problem. Okay, but that's me. And I'm going to drop a rock, which is not in my hand because then my arm would look really long, okay, over the edge of the cliff. So if I'm going to do that, at this point, how fast is the rock going? 0. It's still in my hand. I haven't dropped it yet. And the instant I drop it, its VI is 0. Okay, so I write here that VI is 0 meters. Okay, and it says the cliff is 30 meters above the surface of a lake, which tells me then that my initial height is 30 meters. Okay, the end of the question is down here at splashdown. Okay, what's my final height down here? 0, because I'm hitting the lake. Okay, and the question wants me to find how fast we're going when the rock hits the lake. Okay, so I get a mark for writing down my givens. Right. Since there's no forces being mentioned here, height and speed are changing, I know this isn't a work energy theorem question. Agreed? If this was a work energy theorem question, I'd either be given work or there'd be a mention of forces and distance and all of that kind of stuff. None of that is in here. Okay? In fact, there's no mention or any even reference to any work being done. So if there's no work being done, then there's no change in energy. Okay? Because in a law of conservation of energy question, energy doesn't change. It stays the same. That's why we can say EI equals EF. So that's how we start the question. Okay? My initial mechanical energy will equal my final mechanical energy. Now, yesterday, we learned that you can calculate mechanical energy by adding what two things together? potential energy and kinetic energy, right? That's our sum total. The mechanical energy is the sum total of your potential energy and your kinetic energy. Okay, so what I've got written here is like this roller coaster question up here. Okay. Now, in the situation with the rock, are any of those energies zero? Eva, which ones? Mm-hmm. Actually, nope, that one we'll have, because we have initial height, right? We have potential when we're holding it, but how fast is it going here? Right. So those two energies would be zero. Right? If whatever I would use to calculate EK, which is V, that's zero. And at the end, what I would use to calculate EP, H, is zero. So those two energies have to be zero. Or, if you don't want to think about it mathematically, think about it contextually. I look at that and go, well, it's not moving, and you have to be moving to have kinetic energy, so it doesn't have any, okay? And at the end, you have to be able to fall. It can't fall any further, so it doesn't have any potential. Either way works, okay? Whichever way makes more sense to you. So now that I've canceled off those two forms of energy, now I want to expand this out again by putting in the formulas. Okay, so to calculate potential energy, I want to write m times g times h initial equals 1/2 mv final squared. Okay, I've written now the same thing 3 times, just in different forms. Okay, I initially said my initial energy equals my final energy. And then I wrote out that that initial energy is the sum of these 4 things. And then the next step was, okay, I eliminated some things, here they are, but I'm still saying the initial energy equals the final energy. Okay. All right, now, I have the mass of the rock. I have the initial height, the initial speed, the final height, okay, looking for VF. So this is the thing I don't have. So I need to isolate it. What do I need to do to isolate it?
Divide both sides by half m.
Divide both sides by half of m. What's m divided by m? 1. What happens to m here? It cancels out. You don't have to cancel it out. Okay? You can leave it in there if you want. You have the mass of the rock. You could punch it in. I'm just telling you it actually doesn't make any difference for this question because mathematically it cancels itself. Okay? All right, so next step, now that we've manipulated, is to write out our fully manipulated formula here. Okay? So what I'm going to have is the square root of g times h initial divided by 1/2. You could have the m's in there if you wanted to. Okay? Equals v hat. Right? Because I have to square root to get just v hat. Okay? Everyone follow what I did there? Just a little bit of algebra. Okay? So now if I plug in my numbers, okay, I'm taking 9.81, multiplying it by 30 meters, that was my initial height, and then dividing that by 1/2, and then square rooting. Okay, so square root of 9.81 times 30 divided by 0.5. All right, so when it hits the water, it'll be moving at 24.3 meters per second. So when we were doing work energy theorem problems, it became pretty evident that there was a pattern that we had to follow. And they all worked pretty much the same until we got to the point where we had to isolate whatever variable we were solving for. Okay? Conservation of energy questions are the same. They are very patterned. They're very formulaic. They always start out this way. And then all you're ever going to solve for is H or V, one or the other. Okay? That's all you're ever going to be asked to solve for. It's either going to be HI or HF, and VI or VF, and you'll be given the other three. Okay? So it's always going to be the same pattern. Once you learn that pattern, you really can't go wrong. Okay. All right. Anybody need that one up anymore? All right. I want you guys to try these two here. Okay, see how you do with those. 10 kilograms, sorry, it's so blurry. I meant to fix it, but I didn't get around to it. Okay, 10 kilogram water balloon is dropped from a height of 12 meters. I want you to calculate the speed of the balloon just before it hits the ground. It's basically the same as what we just did. Okay, and number 12, you have a 30 kilogram child on a trampoline jumping vertically into the air at a speed of 1.60. That's 1.60 meters per second. Okay, calculate how high the child will rise. It's the opposite of what we did. Okay, that one you're looking for H and you're given V instead. All right, and this trampoline would be like at ground level. Right, so it's one of those ones that has a hole dug underneath it, so you start from a height of 0. Okay. All right, give you a few minutes to try those on your own. All right, so on number 11, we have the same situation we have with dropping the rock off the cliff, just dropping a big water balloon off the cliff. Okay, so we are going to have, in that question, a mass of 10 kilograms, not that it's going to matter, okay, a height, an initial height of 12.0 meters. Because it's dropped, what's VI? 0. Because we're talking about when it hits the ground, what's our final height? 0, because when you're on the ground, you have no height. Okay, 0 meters, right? And we're looking for VF. Okay, again, there's no mention of forces, there's no mention of work, so we know that this is a law of conservation of energy question. All right, so we'll start out with EI equals EF. My initial mechanical energy equals my final mechanical energy. All of it's going to be converted as the water bomb falls. Okay, so that's going to mean my initial potential energy plus my initial kinetic energy equals my final potential energy plus my final kinetic energy, because that's how we calculate mechanical. We add those two together. Okay, from the context of the question and my mathematical numbers here, okay, I know that initially the object's not moving. If the object is not moving, then it doesn't have any initial kinetic energy. And also from the context of the question and the numbers I was given, I know the final height is 0. That means there's no potential energy at the end. All right, so I've now eliminated two things, which makes my math a lot easier. Okay, now I'm just going to expand out these two terms. To calculate potential energy, I take mass times gravity times height, and to get kinetic energy, 1/2 times mass times speed squared. Okay, so I'm looking for VF. So to get VF by itself, I would divide both sides by 1/2 of m. Okay, I can leave the m's in there if I want to, but I never do, because why? Okay, I would not want to have to enter extra numbers into my calculator and risk making a mistake. Okay, so I'm going to cancel the m's. That solves for VF squared. Okay, so I'm going to square root that. That's going to give me this final formula of G times H initial divided by 1/2 equals VF. When I plug in my numbers, that's 9.81 times 12 meters divided by 1/2, all square rooted. Okay, when I do that, I should get 15.3 meters per second. Okay, making sense? All right, same pattern as the last one. All right, the first 3 steps or so were the same. So if we were looking at what you would get marks for on a question like this, you'd get 1 for your givens. You'd get 1 for recognizing what kind of question it is, in this case, law of conservation of energy. Okay? You'd get a mark for identifying what types of energy are present, even if it's all 4. Okay? You'd get a mark for that. You'd get a mark for your manipulation. Okay? Sorry, that would be here, a mark for your manipulation. Okay? Probably a mark for plugging in your numbers. That's up to 5 marks. Okay? And a mark for your final answer. 5 or 6 marks. Okay, for that question. All right, and the first 3 marks are always the same 3 things. Okay. All right, try number 12. It works very much like this one, except instead of solving for speed, now you're solving for height. Okay, give that one a whirl. Okay, so on number 12, okay, we've got the little kid on the trampoline, so they're at ground level to start with. Okay, and they're going to jump from ground level to a height that we don't know, that we're being asked to calculate. So in that case then, our final height is our unknown. How fast are they going to be going when they get to that height, to their maximum height? 0. Okay, what goes up must come down. Okay, that's the reason for the law of conservation of energy. Okay, if I throw something up in the air, when it gets to its highest point, it's going 0 meters per second. Okay, like this. Okay, if I throw that up in the air, okay, it goes up, it goes up, it goes up, but it's slowing down, slowing down, slowing down, slowing down. When it gets to its maximum height, it's not moving for an instant. Okay, and then starts to fall back down to me. Does that sort of make sense? Okay, now, according to the law of conservation of energy then, if it leaves my hand at 2 meters per second, when it comes back to my hand, how fast is it going? Same, 2 meters per second. Right? It has to have the same amount of energy when it gets back, according to the law of conservation of energy, yes? Okay, that's what it says anyway. Energy can't be created, it can't be destroyed. When it comes back to my hand, it better be going the same speed it left at. All right, so at their maximum height, their VF would be 0. Right? Their initial height is on the ground, so that would be 0 meters. Okay, we know their mass is 30 kilograms, and we know their initial speed is 1.60 meters per second. So we've got enough information to do this. Once again, there's no mention of work, no forces are given, no distances. Okay, so we know it's EI equals EF, okay? EP initial plus EK initial equals EP final plus EK final, okay? According to the context of the question, they start on the ground where there be no potential energy, okay? When they're at their maximum height, they're not moving, so they have no kinetic energy, okay? And this sets up the opposite of the last 2 we did. Okay, now I'm trying to solve for HF. So to get HF by itself, I just divide both sides by m times g. What's going to happen to m again? It's going to cancel out. You can leave it in there if you want, but it cancels out. Okay, and I don't have to square root because HF isn't squared. Okay, so 1/2 times 1.6 squared, okay, divided by 9.81 gives me 0.13 meters. Is that very high? No, like that high. Okay, they're a little kid. Okay, they're on a trampoline. 1.6 meters per second is not very fast. Gravity pulls you down at 9.81 meters per second squared. It's not going to take long for it to eat up 1.6 meters per second. Okay, so that's a pretty reasonable answer, okay, given the context of the question. All right, questions on that one? Okay, we're starting to see the pattern here. Okay, in a situation like this one with the pulley, okay, if I'm holding that system, so I'm holding the 2 kilogram block so that it can't fall, okay, is there energy in that system? What kind? Potential, because if I move my hand, the whole thing's going to go. Okay, the 2 kilogram mass will fall, the 1 kilogram mass will rise. Okay, when I do that, will the energy in the system be conserved? Let me ask you a different way. If I let this go, the 2 kilogram mass will fall. Okay? The 1 kilogram mass will go up. Okay? Does that mean that the 2 kilogram mass is doing work on the 1 kilogram mass? It does. Okay? Because as it falls, it has to accelerate the 1 kilogram mass upwards against gravity. So it's going to give the 1 kilogram mass potential energy, and it's going to give it kinetic energy. Both. Okay? Meanwhile, that 2 kilogram mass is falling, so it's losing potential energy. Okay? It's going to speed up a bit, but some of its energy is being lost, or doing work, on the 1 kilogram mass. Is the energy in the entire system going to stay the same? It is. Okay? The system includes both masses. Whatever the 2 kilogram mass loses is going to be gained by the 1 kilogram mass. So within that pulley system, the energy remains the same. No energy is lost. It's just moved from one place to another in the system. Okay? Once again, energy can't be created. It can't be destroyed. It all is accounted for. It's just not staying with one part. Okay? It's going to a different part of the system, but the entire system's energy would remain the same. Okay? We've already done questions harder than those two. Okay. Pendulum. Pendulum's a good example of the law of conservation of energy. And I just happen to have the world's most ghetto pendulum. Okay? Because I am saving taxpayer money left, right, and center with my awesome roll of tape on the end of my drawstring from my hoodie. Okay? Hey, there's no money in education. There's budget cuts everywhere. This is what you get. Okay? You want something fancier than this, tell your parents to write their MLA. Put more money in education so Coderre doesn't have to take the drawstring out of his hoodie and make demonstrations. I'm just kidding. Okay. So, if we've got a pendulum, okay, if the pendulum's just hanging here, does it have any energy? Okay, in reference to the ground, yes it does. You're absolutely right. But because it can't fall, because I'm holding it and it can't fall, does it have any mechanical energy here? No, this is the lowest point in its swing, right? Now, if I pull it out to here, what have I done? Don't say pull it up to there, Coderre. What have I done, physically speaking?
Gave it potential energy.
I gave it potential energy. Okay, so I transferred energy. What do we call that? 4-letter word, starts with W. Work, right. I just did work, right? I lifted it to here. Okay, now if I let it go, it's just going to start to swing through the arc. And it'll keep swinging because of the law of conservation of energy. Okay, I did work, I gave it potential energy, and once I let it go, that potential energy got turned into kinetic, and then back into potential, and back into kinetic, and back into potential, and it'll just keep doing that, okay, until somebody gets hypnotized and starts clucking like a chicken. Okay, no one's ever done that. I guess I'm not very good at this. Okay, so that's a perfect example of the law of conservation of energy. So good, in fact, that for a very, very long time, this was used to keep time. Okay, anyone ever seen an old grandfather clock? Okay, I mean, they're not very common anymore. Okay, but a pendulum is incredibly reliable for keeping time because it'll reliably, okay, go back and forth, converting one form of energy to another. Now, in the real world, is that going to swing forever? I was actually helping it, so you can see now that I stopped helping it. Okay, it stops swinging fairly quickly. Okay, what did you have to do to an old grandfather clock every day? Anybody know?
Rewind it.
Yeah, you had to wind it up. Okay? Attached to the top of the pendulum was actually a spring. Okay? And so you would crank this thing with a key, okay? And it would tighten the spring so that the spring would always add a little bit of energy on each swing to keep the pendulum going back and forth. So because it wasn't a perfect system, or an isolated system, a little bit of work had to be done on each swing to make sure it always had the same amount of energy. Okay? So it's a perfect example of work energy theorem and conservation of energy. Okay? Incredibly reliable, okay? Kept time for years and years and years before batteries and things like that came along. Okay? Making sense? Okay, so in this example here, number 2 with the football, okay, so this is like the start of the game where the ball is on the ground, right? Okay, it's on that little tee that they use and they start the game by kicking it, okay? So what type of energy does the football have the moment it leaves the kicker's foot?
Kinetic.
Yeah, mostly kinetic. Okay, because I mean it's still kind of on the ground. The kicker's foot is right there. The ball's still on the ground. Okay, but when it leaves the kicker's foot, it's moving as fast as it's going to move at any point. Right, so it's going to have mostly kinetic energy. It's going to have maybe just a tiny bit of potential because it's maybe this far off the ground. Okay, but it also has some elastic potential energy. When you kick a ball, what happens to the ball?
Tries to absorb the force.
Yeah, and in fact, it changes shape, right? Like if you ever watch like a super slow-mo of somebody kicking a ball, their foot goes like right into it, the ball molds around their foot a little bit, okay? That's changing the shape of the ball and putting a little bit of elastic potential energy into it as well, okay? We don't need to think about it in that complex of terms, okay? At this point, the ball has mostly kinetic energy. Now, as that ball goes through its flight, okay, it's gonna make a pattern that looks like an arc, a projectile arc. Okay? Now, when it's here, what kinds of energy does it have? It's got both. It's off the ground and it's moving, so it has kinetic and potential. Right? What about here?
That's the peak of the arch.
Yep. So what kind or kinds of energy does it have there? Has it got potential? It's above the ground, right? Does it have kinetic there? It does, because it's moving forwards. Okay? If I throw something straight up in the air, at its highest point, its velocity and speed are 0. But if it's moving this way, even at its highest point, it's still moving forwards. So it would still have some kinetic energy at that point. Okay? You would have less kinetic energy here than here or here, okay? But it would still have some because it would still be moving forwards. Okay? Everybody all right with that idea? Those are the kinds of things I might ask in a multiple choice question, okay, on a test. Because that tells me that you can look at a situation and analyze it from an energy perspective. Okay, look at a situation and go, oh, okay, well that's moving. Movement means it has kinetic energy. It's also above the ground. Height means it has potential, and be able to come up with an answer. Okay, so that's the kind of thing I would ask in a situational multiple choice type question. Okay. This graph is showing potential energy as a function of height. Okay? What's really, really wrong about this graph?
It's just straight lines.
It's straight lines, okay. There's 2 straight lines, but what's wrong with like the second part of this graph?
Is that potential energy decreases as you get higher.
That's right. Okay, it's saying here that for the first little while, as height increases, your potential energy increases. That's right. This is wrong. Okay, it's saying that at some magical point, your potential energy just starts to decrease, even though your height is increasing. Is that true? What's missing here that makes this graph misleading, that all good graphs should have? Is there a scale there? There are numbers? That makes it a terrible graph. Okay? Because what do we assume? We assume that the numbers get bigger as you go along the x-axis, like a normal graph should. Okay? This graph is fine as long as, okay, we go 0, 10, 20, 30, 40, 30, 20, 10, 0. Then it's fine. Okay? Then there's absolutely nothing wrong with it. Okay? But nobody makes a graph that way. Okay? And so as a result, that graph is very, very misleading. Okay? Would the kinetic energy graph here also be misleading then for the same reason? Yeah. Okay? Like, because it's saying that as you go up, your kinetic energy decreases, and then for some reason it just starts going faster. Well, that's not right. Okay? But it's right if we have the same scale. Okay? And that the highest part of it is in the middle. All right? So the main purpose of these two graphs is to drive home a graphing point. All graphs should have a scale or they'll be misleading. Okay. Don't know where I was going with that diagram. Okay, I want you guys to copy this one down. Okay? This is a very typical law of conservation of energy question, but more complex than the ones we've done thus far. Okay, so I want you to copy it down and then we're going to walk through it together as another example, but a more complex example. Okay, so we've got a sledder, okay, that has a mass of 70 kilograms, okay, and they are at a point that is 30 meters above the bottom of a hill, moving at 1.5 meters per second. And we want to calculate how far above the bottom they are when their speed is 7.5 meters per second. Okay, so I'll give you a minute to get that one copied down. Don't laugh at my picture. You laughed. I said not to laugh. It's okay. I'm a terrible artist and I know it. So if this sledding hill is perfectly frictionless, we're in an isolated system, okay, there's no mention of any forces or work or anything like that in this question, can we assume that all of the mechanical energy is conserved between the top of the hill and the point that they're asking us about? Okay? We have to assume that. Okay? We assume that everything is a perfect system unless we're told otherwise. So what that means for us, okay, in this particular question is that our initial energy is going to equal our final. Okay? Now, that's going to mean expanded out that my initial potential energy plus my initial kinetic energy equals my final potential energy plus my final kinetic energy. Okay? So now I go back to the question and I see, are any of these 0? All right, so it says that they start at 30 meters. That means there is initial potential. They're moving at 1.5 meters per second. Okay, so that means that there is initial kinetic. Okay, because I know this number is HI. I know that VI is 1.5 meters per second. Okay, I'm looking for HF. And I know that VF is 7.5. That means that all 4 types of energy in that equation are not 0. Okay? That there's actually a value for each one. So I can't cross any of them off. All right. I'm looking for final height, which would be part of EP final. So before I put the formulas in, I want to get EP final by itself. So how do I get EP final by itself?
Subtract both sides by EK final.
Right, subtract EK final from both sides. All right, so I'm going to have EP initial plus EK initial. In other words, the mechanical energy minus the final kinetic energy. that should equal the final potential energy. Okay, well that makes sense. Mechanical minus kinetic equals potential, right? Because I usually add the two together to get that. All right, now that I've got that, now I can expand it out again. Okay, and I can say, all right, m times g times h initial plus 1/2 mv initial squared minus 1/2 mv final squared. Okay, so I'm just putting in the formulas for each of these energy types equals m times g times h final. All right, I want to get h final by itself. What do I have to do with the m and the g? Divide them over to the other side. Now, can I cancel the m? The answer is yes, I can. Every single term in that equation has m in it. Okay, and it's being multiplied in every single one of those terms. That means it doesn't matter what m is. Okay, m affects each term the same way. So you can take m out of this equation, or you can leave it in. It doesn't make any difference. Okay, I'm going to cancel it because I don't want to bother typing it and writing it. Okay? So now that m is gone, I want to get hf by itself. I only have to divide now by g. Okay, so now hf is by itself. I just have to plug in my numbers, right? G is 9.81. My initial height was 30 meters. 1/2 times my initial speed squared, which was 1.5, minus 1/2 times my final speed, which was 7.5, squared, divided by g. That's going to give me my final height. Okay. Is it still the same pattern? Okay, still the same pattern we used for the simpler questions. It's just this time, none of the values were 0. I had to account for all of them. Okay. Does it look a bit more involved from an algebra perspective? Yes. Okay. I'm not going to lie to you. That's complex algebra. You got to move a lot of things. Okay. All right, so we're going to have 9.81 times 30 plus 0.5 times 1.5 squared minus 0.5 times 7.5 squared divided by 9.81. Okay, so they will be at a height of 27.2 meters. They didn't go down very far, did they? They only descended 3 meters vertically. Okay. Okay, so you'd get a mark for your givens. You'd get a mark for conservation of energy. You'd get a mark for identifying what types of energy were involved. A mark for your manipulation. A mark for your plugging in the numbers. And a mark for your answer. Okay, is that 1, 2, 3, 4, 5, 6? Okay. Everybody all right with that? That's as tricky as they get. Having all 4 energy types and having to solve for either your final height or your final speed. Okay, but the pattern's the same. As long as you can learn the pattern and figure out what types of energy are involved, they all work the same. Okay, I'm going to give you a 5-minute break here. All right, I'm going to put another question up here and I want you guys to try and solve this. So we can work a lot like the sledding question, except instead of solving for the final height, you're going to solve for the final speed. Okay, so you're going to have a roller coaster. Okay, so here's the situation. The roller coaster is at the top of the first hill, which is 45 meters above ground level. And it is moving at 3.5 meters per second. I want you to calculate how fast it's moving over here when it is 12 meters above the ground. Okay? And you can assume it is an isolated system, okay? So there's no energy lost or gained. Okay, so just so you know, from a context of a question perspective, sledding down a hill and roller coasters are always conservation of energy examples. Okay, so if you run into a question, a quiz, or a test, and it's like, oh, roller coaster does this, or there's a kid on a sled, it's a conservation of energy question. Okay, if it's, you know, a truck is pushing a rock and is mentioning force and distance, that's a work energy theorem question. Okay, that's how you tell the difference. But from a context question, roller coasters and kids on sleds are going to be your conservation of energy questions. All right, so what we know here is that the energy at the beginning is equal to the energy at the end. Okay, no energy is being created or destroyed, gained or lost in this situation. At the beginning of this question, we are 45 meters above ground level. That means we have initial potential energy. We are also moving at 3.5 meters per second, which means we have initial kinetic energy. At the end of this question, we are 12 meters above the ground, which means we have potential energy. And we are still moving. We have to be because we're lower than where we started, which means we have kinetic energy at the end. Okay? None of those are zero in this question. Since I'm looking for the final speed of the roller coaster, I want to isolate that term. Okay? I want to isolate my final kinetic energy because that's what will have VF in it. So to do that, I'm going to subtract EPF from both sides. If you don't have this done, make sure you're writing it down as we go so that you have at least one solved example. Okay? So we're going to go EP initial plus EK initial, okay, minus EP final equals EK final. So we're saying the mechanical energy initial, that would be this part, minus the potential energy final will give me the kinetic energy final. All right, now I'm going to expand that so that all the formulas are in there. So that's going to be M times G times H initial plus 1/2 MB initial squared minus M times G times H final, so this one, equals 1/2 MB final squared. Okay, I gave you the mass, but do you need it for this question? No, it's going to cancel off. Okay? It's in every term, so we're going to get rid of it. Okay, when would I need to keep it? The answer is I have to keep it if I'm not asked to calculate a speed or a height, but instead asked to calculate what's the kinetic energy at the end. I have to keep mass in if I want to calculate energy because it's kilogram meters squared per second squared, or joules. Okay? The speeds and the heights are only dependent on gravity. Mass doesn't matter for those. Okay? So that's why we can cancel mass in all of these. All right, so now looking for VF. To get VF by itself, I would divide both sides by 1/2 and then square root. Okay? So when I plug in my numbers, I'm going to have 9.81 times 45 plus 1/2 times 3.5 squared minus 9.81 times 12. Okay, so all those terms in there divided by 1/2, all square rooted to get VF, which comes out to 25.68 or something like that. That's 25.7 meters per second. Okay, and that answer makes sense because it's lower, it should be going faster than it was up here. Okay? you've now seen one example of finding final height, or finding height when you're given everything, and finding speed when you're given everything. I will ask one or the other on the unit exam. Okay, this question, that could be a unit exam question. The last question with the kid on the sled, that could be a unit exam question. That's the kind of question I'm gonna ask. Okay, I might even make it easier than that. I might, on a unit exam, instead of asking about this position, ask about this position. How would that be a little bit easier? Right, this number here would be 0. Okay, so you'd have one less thing to punch into your calculator. The method is all still the same, the pattern's all the same. Okay, you just have 2 less numbers to punch in your calculator. Okay. All right, we're going to work on this tomorrow. We're going to do a unit exam review on Friday. I'm going to see where we're at after tomorrow. If we're doing good with this after tomorrow, then we'll do a lab on Monday. Okay? If we're not, then we'll spend Monday on this and work energy theorem. Tuesday, okay, will be efficiency and finishing anything else up that we need to finish up. Wednesday is your test, right? Yeah. No, that's wrong. No, Tuesday's your test. Tuesday's your test. We're definitely not doing the lab. Yeah, we'll do that maybe on the last day before Christmas or something. We'll figure it out. We might not do it at all. Okay? Yeah, so your test is Tuesday. So this tomorrow, unit exam review Friday, efficiency and this stuff on Monday, test on Tuesday. Okay? Should you expect to see a work energy theorem and maybe a question like this on your quiz tomorrow? I would bank on it if it were me. And it is me. I'm the one who's going to decide it. And I decided. So, have a look at that tonight. Okay? Should be pretty straightforward. Okay? Work labs are looking good. About a quarter of the way through them. They look pretty good so far. Okay? We'll talk about those tomorrow as well. All right, done for today.